X-ray diffraction. Crystals began being closely examined in the 17th century. Many scientists came after. In the 1880s, the crystal structure was finally able to be verified with the use of X-ray crystallography. What is X-ray diffraction? An analysis tool used to indicate the crystal structure of many unknown crystalline organic and inorganic molecules. How does X-ray diffraction work? Electromagnetic X-rays strike electrons, which produce secondary spherical waves coming from the electron. The X-ray striking is known as elastic scattering, and the electron is known as the scatterer. The diffraction of X-ray beams by the crystalline atoms. The diffraction occurs in many different angles and intensities. The variety of diffraction angles and intensities gives insight into what the 3D molecule looks like at an atomic level. Why does this work? The waves add constructively and cancel each other out destructively. This is seen by the Bragg's equation. This diffraction works partially because the wavelength of the X-ray is usually the same order of magnitude as the spacing. So what's the point? Many salts, metals, and semiconducting molecules form a crystalline structure, benefiting the popularity of X-ray diffraction in the scientific field. In chemistry,
in order to use ladder diffraction and XRD, X-rays must be as close to monochromatic as possible. The X-ray tube does this by producing limited frequency ranges of high-intensity X-rays. Filters, monochromators, and software are also used to further refine the frequency of the X-rays for analysis. Shown here is a figure of a typical X-ray tube. The electrons generated come from a tungsten filament that is not shown here in this figure. The filament current is usually set around 25 to 40 milliamps. The anode is usually made out of pure metals such as copper, molybdenum, iron, or chromium. Cooling water is circulated around to keep the X-ray tube from overheating. A high potential voltage of 30 to 40 kilovolts is maintained at the anode in order for the generated electrons to be accelerated so that it interacts with the incoming X-rays. The electronic equipment is also used at the anode to maintain a ground potential and a high negative potential on the cathode. Shown here in Table 1 are characteristics of common anode materials for chromium, iron, cobalt, copper, and molybdenum. Depending on the experiment, these should be selected so that their advantages overcome their disadvantages. For example, if you were to analyze an organic material, you most likely want to use copper. Taking a look at a monochromator, it's the most common way for X-rays to be filtered. It could either be used on the primary or the diffracted beam, which makes use that each wavelength is directed at a single crystal of known orientation and d-spacing that will be diffracted at discrete angles according to Bragg's law. This allows you to choose a crystal with d-spacing to focus only on the desired radiation. The undesired wavelengths are then dispersed.
One of the uses where X-ray diffraction can be used is to perform protein crystallography in order to visualize the tertiary structure of the molecule. The first protein structure in the history was determined by using the technique of protein crystallography. It was determined for a protein myoglobin by the experiment performed by two famous scientists who received a chemistry Nobel Prize for that in 1962. Since then, scientists have been receiving Nobel Prizes for determining different protein structures by using one of the diffraction methods. Protein X-ray crystallography is one of the few methods which provides tertiary protein structures at atomic resolution, which other techniques cannot do efficiently. This is the reason why it is considered one of the dominant methods in the field of structural biology, where 80,000 protein structures out of 90,000 entries in the protein data bank are determined by diffraction methods. The general idea is to pass an X-ray beam through the crystals of protein where light gets diffracted and forms a pattern corresponding to the structure of the crystal. This pattern can further be mapped onto the electron density map, which can be used to visualize the exact arrangement of atoms in the crystal to assemble a complete tertiary structure of the particular protein by a computer. Due to their irregular shape and complexity, proteins are really hard to crystallize. To perform an efficient X-ray diffraction, we will need a pure and homogeneous target protein to grow out the crystals. Numerous attempts need to be made in order to obtain a crystal large enough to perform an experiment. There are several conditions and factors that play a role in growing the accurate crystals for the method. The concentration of the components of the solution can be varied to scale up the expression and purification. Slight pH changes or temperature can affect the crystallization. Additions of detergents or metal lines can enhance the process. Buffers like polyethylene glycol and salts like ammonium sulfate can be added to supersaturate and salt out the proteins to form large crystals, which could take from several days to several weeks to grow. Crystals need to be mounted in a way where the sample can be raised so that X-ray beam can be passed through the sample. So crystals get mounted in a capillary tube at room temperature or get flash cooled to 100 Kelvin in a loop. They are further attached to a device called goniometer to enable an accurate position for the sample. It is needed when X-ray beams are emerged from a narrow tube called collimator to strike onto the crystals. Goniometer changes the sample angles from 30 degrees to 180 degrees to produce diffraction pattern at different angles. Diffraction pattern gets created by sharp spots with their relative intensities and gets recorded using regular photography film by X-ray detector. For high resolution and luminosity, synchrotron is used as an X-ray source where intensity is greater and therefore data collection times are shorter. The intensities of these spots on diffraction pattern are used to calculate the electron density of the molecules within the crystal. The electron density map is the 3D structure obtained and created with the help of a computer to find the exact location of the atoms and build a complete final structure of the molecule.
X-ray diffraction to metallurgical science. Metallurgy is a study of physical and chemical behavior of metallic elements. Early knowledge of metal structures was limited to optical microscopy. It was recognized that the structure of metals was essentially crystalline. 1920s and 30s was the main decade X-ray diffraction was applied to solve metallurgical problems. It determined that the majority of metals crystallized in one of the three typical metallic structures. Metal matrix composites are of interest due to several advantages in terms of mechanical properties and easy fabrication. These materials are used in the aerospace, aircraft, automotive, and many other manufacturing and industrial fields. The interest in the deformation of single crystals of metals in tension or compression led to an examination of the behavior of metal crystals in the industrial operations of rolling, drawing, swagging, etc. Modern X-ray diffraction analysis has developed into a reliable method for the quantification of mineral and material phases. It can therefore provide important information of the mechanics and kinetics of metallurgical reactions. X-ray diffraction is used in the determination of the crystal structure of identified materials, the identification of single-phase materials, minerals, chemical compounds, ceramics, or other engineered materials. In metallurgy, it is a quantitative determination of amounts of different phases in multi-phase mixtures by peak ratio calculations. An example of metal matrix composites used in metallurgy is steel, an iron-carbon alloy. During X-ray diffraction, steel is treated with a suitable acid to dissolve the iron matrix and leave insoluble carbide residue, which can be submitted to chemical and X-ray analysis. Information on solid solutions is gained from the positions of the diffraction spots or lines. The positions of the diffracted spots or lines correspond with a mean value of the lattice spacing, which is used in the phase boundary determinations and equilibrium diagrams.